Hello everybody and welcome to Chapter 7 of Chemical Structure and Reactivity. I'm your host Palladium, and today we're going to go over transition metals and their complexes. Once again, on this front slide we have the shoutout list. If you want to get added to the shoutout list, you can either DM me on Discord or leave a YouTube comment. I'd be happy to add you. So let's get straight into this. What exactly will we be talking about? I already mentioned transition metals, but we'll also go into their complexes. And these transition metals, such as iron, manganese, and copper, can bond with ligands and therefore form complexes that have many different properties that can be observed, such as magnetic, spectroscopic, and also many other properties that we will cover in this chapter. Now, one real-world application of using metal complexes is found in cisplatin, which is an anti-cancer drug that prevents the replication of cancer cells as it binds to DNA. Therefore, it's become a popular chemotherapy drug. Anyways, let's take a quick look at the periodic table. So you can see we have some empty boxes and we have some boxes that are filled in with the elements. Now, those empty boxes were the main group elements, which was covered in the last chapter. However, we're focusing specifically on the transition metals, which are found in the D block of the periodic table. Now, here's a quick note. If you watched my past lecture in chapter 16, you would have noted that group 12 is somehow included as a transition metal. Now, according to the authors, it's characterized as a main group metal. However, we still group these metals, which are zinc, cadmium, and mercury, into the D block. Now, here's what I like about this chapter. Compared to the last chapter, I went over the main group elements and how they can form a multitude of compounds, which, don't get me wrong, is pretty cool, but it does get boring at times. And so this chapter will go more about those specific complexes rather than just the elements on their own. Now, what's looking at elements without looking at their orbitals? So, here is a graph shown to the right of 4 specific orbitals and their energies across the 4th period of the periodic table. We have 3p, 3d, 4s, and 4p orbitals, and their energies all steadily decline as you grow across the period. Now, we can see that for the 3p energies, 3s is not shown here, they fall rapidly. And that's because they experience a stronger pull from the nucleus as they're not shielded. If you remember back in chapter 2, I introduced the concept of shielding or screening. Shielding is essentially what happens when core electrons block the true nuclear charge from ever reaching the outer electrons, meaning that we get essentially an effective nuclear charge instead of the real one being used. Anyways, going on about the orbitals, we can look at the 4s and the 3d orbitals. Now, we can see that the 3d orbital has a lower principal quantum number, which is 3, and the 4s orbital has principal quantum number of 4. But if you look at the electron configurations for these 4th period elements, then what's going to happen is that electrons are going to be filled in the 4s orbital first, even though it has a higher principal quantum number. Now, that specifically is because s orbitals are more penetrating than 3d orbitals. Now, what do I mean by penetration? Back in chapter 2, the authors discussed what penetration was, which is the ability of an electron in an orbital to very much reach the nucleus and experience its positive charge. Now, because its electrons are more penetrating in 4s orbital, it's lower in energy and is going to therefore experience a greater effective nuclear charge. Going on to the slopes, or how steeply these energies fall down, we can see that the energy of 4s doesn't fall as steep as compared to 3d, and that's due to shielding. Now, here are two main exceptions that I want you to focus on: chromium and copper. And to understand what it looks like, we have to look at the 3D energies. We can see that there are essentially two peaks that correspond to chromium and copper while looking at the energies of the 3D orbital. Now, that lies in their electron configurations. So, for the copper atom, we would expect an electron configuration of argon 4s2 3d10. And for chromium, we get argon 3d4 4s2 for our expected electron configurations. However, that's not true, as both elements take one electron from the 4s orbital in order to either completely fill or partially fill the 3d orbital. And the reason why this is observed and why this deviates from our expected electron configuration is because it increases the favorable electron exchange interaction. And because of these unexpected electron configurations, electron-electron repulsion will be changed. And therefore, we're going to get essentially these two little blips in the 3D energies. Now, if 3D is lower in energy than 4s, then why don't electrons just go from 4s to 3D? I mean, it makes sense as everything in the universe wants to get to a lower energy. However, the issue is that if we had the two electrons from 4s move into 3D, then there would be greater electron-electron repulsion, meaning that energy is actually going to be higher. And of course, in the universe, we don't want higher energy. We want it to be lowered. Now, here's a quick thing about orbital energies. So, in chapter 12, which was actually chapter 2, I accidentally put that typo there, but in chapter 2, we said that the ionization energy of an electron was approximately the negative of its orbital energy. And it conceptually makes sense, because if we remove an electron with some amount of energy, then we must have overcome that orbital energy barrier. So we can just say that the ionization energy is the negative of the orbital energy as a quick approximation. However, here's the thing. Once an electron is removed, those orbital energies will change due to reduced repulsion once we remove those electrons. And because of shielding from the 3D electrons, those 4s electrons are going to have this effect where they are going to make this first and second ionization energies increase gradually from the transition series, as you can see in the graph on the bottom. Going on about charges, we did mention that oxidation states were going to be useful in other chapters, such as chapter 16. So here's a quick disclaimer. When we're going to be using oxidation states in this chapter, this book, etc., when we have specific metals such as manganese and +7 oxidation states, we don't actually have manganese 7+ ions. That's not going to happen. However, the oxidation state is simply a way to count electrons and is therefore useful in redox reactions. Now, here's also another quick note. Since the 3D orbitals contract and fall in energy as we go across the transition metals, ionization and covalent bonding are going to get harder for transition metals as compared to nonmetals. Now, here's the moment that we've all been waiting for, complexes. So complexes come in a variety of different forms. We have simple tetrahedral complexes, such as in complex A, we have square planar complexes, octahedral complexes, weird octahedral complexes, and overall just complexes that come in so many different forms and shapes. And corresponding the coordination number to geometry, 6 coordinate complexes usually have an octahedral geometry. Meanwhile, 4 coordinate complexes can either have square planar or a tetrahedral geometry. And here's a quick note about complexes. The interaction between a metal and a coordination ligand, it's not going to be as strong as a covalent bond between two nonmetals. But regardless, it is strong enough that it's going to be stronger than a non-bonded interaction or an intermolecular force. Going on about ligands, ligands can come in many different shapes and sizes, but one way to classify them is through a concept known as denticity. Now, that name should ring at least a bit of a bell, and that's because this word comes from the exact same root that is used in words such as dental care or dentistry. And you may be wondering, what does this have to do with teeth? Well, if we have a ligand, then denticity is defined as the number of atoms that can donate electrons to these complexes. And so one good way to remember the denticity of a ligand, what it is to imagine how exactly or how many ways can we have these ligands essentially bite down on the metal ion. And that's exactly why we give it that name, because we imagine it biting down on that metal ion. Going on about the geometry of complexes, complexes exist in isomers, much like organic compounds, which I did discuss back in chapter 15. So, for example, for this specific complex, we have both a trans and a cis isomer. Complex A on the left shows the trans isomer, where we have the chlorine atoms at 180 degrees to each other, or opposite sides. Now, complex B is going to be the cis isomer, as those chlorine atoms are essentially going to be quote-unquote on the same side. And therefore, we're going to have a cis isomer. Now, here's something interesting about this complex. There are only 4 ligands. So, to somebody who doesn't know complexes that well, you would assume that the geometry would be square planar or tetrahedral. No. And that's because this EN ligand, which stands for ethylene diamine, that is bidentate, meaning that it's going to have 2 atoms that are going to chomp down on that metal ion. And therefore, we're going to have a coordination number of 6. And therefore, we're going to obtain an octahedral geometry. Going on about octahedral complexes, we can actually look at the molecular orbitals caused from sigma interactions. Sigma interactions are essentially what happens when you have head-on overlap of orbitals. And we can see that in this figure to the left, we have many different orbitals, both atomic and symmetry, that specifically correspond with each other in terms of symmetry and are grouped up into groups such as A1G, T1G, T2G, and EG. Now, as for why these are given these names, I personally have no idea. And that's mainly because grouping these orbitals based on symmetries is primarily based on group theory, which we don't have enough time to get into, but we do have a brief explanation of them back in chapter 3. Anyways, let's talk about what we're going to do next with the symmetry and atomic orbitals. Now, since we already grouped them into different symmetries, using the principle that only orbitals with the same symmetry can interact, we can build a molecular orbital diagram. And what we see is we're going to get bonding molecular orbitals whose main contribution are going to be from ligands. And in addition, we're going to get some non-bonding atomic orbitals from the metal. Meanwhile, we're also going to get some anti-bonding molecular orbitals from the metal. And finally, at the top, we have anti-bonding molecular orbitals, which come from the metal. So what you need to know is that when ligands donate electrons into these bonding molecular orbitals, that complex will be further stabilized and will get its energy lowered essentially. Now, when we're talking about ligands donating electrons to these complexes in terms of the molecular orbital, they donate these through sigma-type orbitals, or head-on overlap. And they go into these bonding molecular orbitals, as I said in the last slide, therefore improving the stability of the complex. Now, there's one specific split, I could say, between these two particular orbitals, EG and T2G, as shown in the diagram. And that's because T2G is the highest occupied molecular orbital, and EG will be the lowest unoccupied molecular orbital. And so the gap between these molecular orbitals, known as the octahedral splitting energy, will affect the physical and chemical properties of these complexes. This will be later explained when we talk about crystal field theory. Alright, that's enough talking for now. Do we have any questions so far in Lectureland? Okay, remind me why T2G is non-bonding. Well, that's going to be mainly because how that orbital is going to be arranged, right? Their spatial orientation, it will be directly between the ligand axes. And when we're looking at head-on overlap, this sigma bonding in metal complexes, it's not going to interact with the sigma bonding in any form. And so therefore we just classify that as non-bonding. If I do remember correctly, I don't know the exact symmetries that well. Alright, let's keep going on. So, in addition to sigma donation, we're also going to get pi donation when it comes to ligands. And this occurs when ligands have p orbitals that are assigned, that are aligned at right angles. And because of these p orbitals, for example, in halide ligands, what's going to happen is that these ligands can get involved in pi interactions with the 3D orbitals. And therefore, we're going to get even more symmetry orbitals with T2G symmetry. Now, there are both ligands that donate pi electrons and accept pi electrons. So, for something such as a molecule that has pi bonding in it, right? If we have a molecule, then there can be pi antibonding orbitals that have higher energies. And these pi antibonding orbitals can actually accept electrons from the metal and therefore interact with the T2G orbitals in the complex. That's enough about pi interactions for now. Let's talk about the octahedral splitting energy. So as I said, this is essentially going to be the gap in energies between the T2G and EG orbital. And if we have some metal in some particular oxidation state, then there has to be some sort of series that affect the octahedral splitting energy. And in fact, we do have one, known as the spectrochemical series. And you can see in the top right, as we go along the series, that octahedral splitting energy is going to get bigger, bigger, and bigger. And that's because, compared to something such as the iodide ion, something such as carbon monoxide is going to yield a stronger sigma interaction, which is going to increase that splitting energy. However, for something such as pi interactions, if we have a ligand that engages in pi interactions more than sigma, then the splitting energy will actually decrease. However, splitting energy does not always have to be affected just by the ligands. Generally, as the oxidation state increases in a metal complex, the splitting energy will increase. Now, typical values for splitting energy are usually going to be from 80 to 350 kilojoules per mole. And in fact, this splitting energy can affect the nature of bonding within these complexes. So, for example, if we have a very low splitting energy, we yield high spin complexes. And these are complexes where essentially the number of parallel spins is going to be maximized. However, if we have a very big splitting energy, then we're going to have low spin complexes, where that energy gap is going to be so huge, the amount of parallel spins is not going to be as big as something such as high spin complexes. And you can see it both in the diagram to the left and also the diagram at the bottom. Now, if you're trying to remember this for an exam, here's a general rule. Weak field ligands, such as bromide, iodide, or thiocyanate ions, those are weak field ligands that will create high spin complexes due to a small splitting energy. However, ligands such as carbon monoxide will have a larger splitting energy, meaning that you're going to get a low spin complex. So weak field, high spin, strong field, low spin. And because of spins in these complexes, we can observe magnetic properties. Now, generally, for first-row transition metals and complexes, the strength of magnetism is proportional to the square root of n times n plus 2, where n is going to be the number of unpaired electrons. And the exact magnetic moment is going to be in the units of Bohr magnetons. Now, there are complexes that are magnetic due to parallel spins or unpaired electrons, but there do exist certain complexes that don't have any unpaired spins. And because the spin of an electron is directly linked to magnetic properties, if we don't have any unpaired spins, if those spins are all paired, then that complex will be diamagnetic and will therefore not interact with the magnetic field. Not only does the octahedral splitting energy both affect spins and magnetic properties, but it also affects spectroscopic properties. And that's because if we look at something such as IR spectroscopy, right? When we shoot some sort of photon at a complex or some sort of molecule, then there is a possibility that that compound will absorb the photon and electrons can jump energy levels. And based on the octahedral splitting energy, different photons at different wavelengths can be absorbed. And that's going to be because of the splitting energy being changed. At the bottom here, we have UV-Vis spectra of a few different complexes. And so, for example, the nickel aqua complex shown in green, that's not going to absorb any photons at the green wavelengths. And so once we have that in solution, we're going to get a green color. And overall, these complexes can form many different striking colors too. On a quick side note, these complexes, because they often have unpaired electrons, can be classified as free radicals. For those who don't know, free radicals are essentially just reactive species that have unpaired electrons. However, although we can technically classify these complexes as free radicals, they're not really reactive. And that's because the unpaired electrons are in metal-based orbitals, such as T2g, Eg, etc. And those specific orbitals are going to be buried inside of the complex, which means that they're not going to be as readily accessible and available. Hold up 1 second. All right, and here is a quick departure for complexes, and we're going to briefly talk about transition metal ions here. And you can see, based on the number of d electrons, if we ionize these compounds to a certain extent, then what's going to happen is we're going to get some we're going to get a double dip structure in these graphs. Anyways, going on to octahedral complexes, let's first look at an octahedral complex where the ligands have pi notation. Pi donation. And so, the complexes without any d electrons will be the most stabilized, while the complexes with the most d electrons are going to be the least stable. Looking back at that graph I showed you from the experimental data side, hydration enthalpies and lattice enthalpies follow that same double dip trend as octahedral complex stability. And that's mainly going to be because they are surrounded by 6 ligands in both water and crystal form. And in fact, bond lengths also follow this trend, as if you have greater stabilization in complexes, you're going to have shorter bonds, while less stabilized complexes have longer bonds. That was enough about octahedral complexes for now. Let's talk about tetrahedral and square planar complexes. So, tetrahedral and square planar geometries are also common for metal complexes, in addition to octahedral. and their properties depend on the energies of the d orbitals in the metal. Now, for these specific geometries, splitting is still present. However, it's going to be much smaller as compared to octahedral. And regarding the geometry, the battle between square planar versus tetrahedral will depend on the amount of d electrons present. Alright, that should be enough for now. I'll let y'all ask any questions in the chat for a second time. Alright, looks like we have somebody typing so far. Okay, yeah. We got a question from Stereochemistry Hater. Well, yeah, that's very much one of the issues for treating ligands as pretty much point charges in crystal field theory. Because, yeah, certain geometries do come from steric constraints. It's just an assumption to make rationalizing metal complex bonding easier. And that's primarily how I learned metal bonding, but regardless, molecular orbital theory is still the way. But anyways, going on about crystal field theory, this is another way to describe metal bonding without having to go into molecular orbital theory. And in fact, if you're in the US, this is primarily how you're going to determine the bonding of electrons in metal complexes and how they affect physical properties instead of MO theory. And so our assumption is we're going to treat the ligands as negative point charges that repel the d electrons of metals. And for a complex such as an octahedral complex, those d electrons are going to split into T2G and EG sets. And the separation between them is of course going to be the octahedral splitting energy. However, one major issue of crystal field theory is that it fails to produce any reason as to why different ligands have different octahedral splitting energies. And molecular orbital theory is overall a lot more general, and although it seems harder than crystal field theory, it is overall better for describing bonding in these complexes. Now, that's enough about metal ligand complexes. Let's talk about a specific class known as organometallic complexes. And you can see we have an absolute bunch of them here. For example, we have ferrocene, we have organometallic complexes with carbon-based ligands that bond to chromium, iron, cobalt, platinum. It's overall really, really cool. And in fact, you can see that that first complex, right? Complex A, that's essentially going to be Zeiss salt, which is a very interesting compound to learn about. However, with the introduction of organometallic complexes, we have to know about the concept of hapticity, which is different from denticity. Remember, denticity is the amount of atoms that essentially bite down on the metal ion and are able to donate electrons. However, hapticity is the amount of atoms in the ligand that are within bonding distance of the metal. And so if you take something such as ferrocene, which is complex D, then the hapticity of that ferrocene ligand, that's going to be it's going to be pentahapto. Now, going on, organometallic complexes generally follow a rule known as the 18 electron rule, which essentially dictates how stable those complexes are going to be. And it turns out, if we have complexes that can lose electrons to have those 18 electrons, then of course they'll readily give them up. And it's important to note that organometallic complexes that obey this rule are diamagnetic. And that's because this rule stems from a total of 9 bonding molecular orbitals. 2 electrons for each molecular orbital, that's going to yield 18 electrons. If we have all those bonding MOs filled, then that complex is going to end up being diamagnetic. And when it comes to counting electrons for determining the stability of an organometallic complex, we can count them in a few different ways. So for example, with charged ligands, we can count benzene as a ligand with 6 electrons. We can do on the other end something such as carbon monoxide as a ligand, that's going to be 2 electrons. And by adding up these electrons, we can determine the stability of an organometallic compound. And of course, this is a great general rule for looking at the structure and stability of these compounds. And in fact, we can see this in the example of MnCO5, which has 17 electrons. And because it has an odd number of electrons, we get a free radical, and that free radical can dimerize. However, there do exist certain complexes that have 16 electrons, and these complexes are actually stable with a square planar geometry. And in fact, we can go beyond 18 electrons into even more anti-bonding molecular orbitals. We can put electrons there. And that's because even if we lose stability, they're only moderately anti-bonding. Now, remember when I told you guys that carbon monoxide can act as the ligand? Well, carbonyl complexes can actually be observed using iris spectroscopy. And that's because it can be used to look at how fast or what frequency the carbon-oxygen double bond stretches in these complexes. Now, when it binds to a metal, its stretching frequency will decrease. And that's because the bond is weakened. Now, why exactly? Well, this is primarily due to pi back donation, where the metal will donate electron density into the pi anti-bonding orbital. And so that bond will get weakened, and therefore the stretching frequency will decrease. In fact, when we have CO ligands that bridge metals to metals, they're even going to have lower stretching frequencies because we're going to have 2 different metal ions, and those metal ions, they're going to give even more electron density into the pi antibonding orbital. And here's going to be the final stretch of this lecture. So, when we dissolve the transition metal ion in water, aquo complexes can form, where water is going to be a ligand. Although it is a weak field ligand, there are many interesting complexes to be seen. So, for example, we can see that chromium forms an aquo complex in water. And these species, such as the chromium species, they have great acidity. And as the charge on the metal increases, the bond between the oxygen and hydrogen, when we're looking at the water as a ligand, that will decrease. And because that bond strength decreases, we're going to have more free protons in solution. Therefore, acidity will increase. Or in other words, the pH will decrease. And here is a quick fact. For the chromium 3 ion, if we hydrolyze that, we're going to yield polymer formation instead of some sort of simple hydroxide. And so we're going to get dimers, trimers, and a whole lot more. Anyways, going on to high oxidation state species, such as those formed by vanadium, we can see that we get complex structures in water. And these oxoanions appear like p-block oxoanions. Now, just for a quick recap of everything, here are 5 main points that you need to know. Transition metals have orbital properties that can change their own properties. Molecular orbital theory can describe complex bonding. Complexes can display a range of properties using molecular orbital theory. Crystal field theory is simply a convenient way to describe complex bonding. And complexes have specific interactions. And so that's going to be the end of chapter 17 for y'all. And so the next chapter, I accidentally put mechanic there, but the next chapter will go from inorganic chemistry and into quantum mechanics. And this will also be tied into spectroscopy and also one of my favorite scientists of all time. And here is a quick gift for y'all. Since the next chapter will involve a lot of math, in addition to a slideshow that I'll prepare, I will also prepare some LaTeX notes, which can also be downloaded and used as a quick reference if you ever want to study some basic quantum mechanics. All right, that's the end of it.